Hello everyone and welcome to the review video for exam 1. I'm going to try and get through this as quickly as possible, both for your sake and for mine. The basic gist here of the video is I'm going to go through all of the slides that cover the material for exam 1, and I am going to point out the stuff that is very important that will definitely be on the exam that you should study. I'm going to point out a very few things that I don't think are quite as important and you can leave out of your studies, and then just comment on the rest, and I won't necessarily tell you on the rest of the stuff if it will be or won't be on the exam. There'll be a few things in that category as well. But I will definitely point out a majority of the topics that will be on the exam. So you will leave this video knowing the topics of the majority of the questions of the exam. I won't just straight up tell you the questions, obviously, but for example, here at the beginning of this chapter, when we get through this stuff here at the beginning, where it's just rehashing stuff from Gen Chem 1, I'm not going to have that stuff on the exam, but intermolecular forces, this is 100% on the exam. If I remember correctly, I think I put four different questions where I give you a molecule and you have to tell me which of these four intermolecular forces are present or are possible to be present with that molecule. And so again, I guarantee it is on the exam. You will have to do that. So obviously, you should learn how to recognize these four intermolecular forces. What needs to be present for a molecule to have those. So the first one there, dispersion forces, everything can have that. So that should be an answer on every single one of the molecules that I give you, is dispersion forces. Dipole-Dipole. You will need to know how to recognize dipole-dipole forces when those are possible in a molecule. So you will have to remember the cutoff between nonpolar and polar. So that was if you have a difference greater than 0.4 between the electronegativities of the two atoms that are connected together. So 0.4 and less is nonpolar, greater than 0.4 is polar. You will not have this chart on the exam just because there's only a certain number of things that I can include there, and this was not one that I could put in there. But the basic gist of this thing is really in these two questions here, and really, it's really kind of this one too. These are kind of together. Do you have polar bonds? And then really the next question just is it a completely symmetrical molecule? And that's really what these two questions are together are asking is, if you have polar bonds and it is not 100% symmetric, then it is going to be polar. You should also be able to recognize hydrogen bonding when it is present. So this is when you have a hydrogen bonded directly to a fluorine, oxygen, or nitrogen. Then you can have hydrogen bonding. And then ion dipole. This should only be given as an answer if I give you an ionic compound as the compound that you're looking at. And you know how to recognize those because those are always going to have a metal and a non-metal. So if it has a metal in the molecule, ion dipole is a possibility. Okay, surface tension, viscosity, and capillary action. I did not put in short answer questions where you have to explain what each of those are, but I do expect you to know that as intermolecular forces increase, these three properties also increase. So these things are due to intermolecular forces for the most part, and so they will increase as the intermolecular forces increase. So now we're getting into talking about what causes vaporization, and condensation, in the energetics of those things. I do expect you to know how to use heats of vaporization. So if I give you some amount of a material and say, how much energy does it take to vaporize this? And I would have to give you the heat of vaporization as well, because I don't expect you to have those memorized. But you should be able to use the heat of vaporization, essentially. Here we're talking about dynamic equilibria and how it relates to the vapor pressure in a closed system. The Clausius-Clapeyron is not going to be on the exam. So that is our first thing that I am just going to tell you now. It's not on there. The Clausius-Clapeyron is a useful equation for certain situations. I think it's more limited in its use than some of the other stuff, and so I left it off of the exam. Now we're talking about sublimation here. I do expect you to, at the very least, understand what sublimation is. So there could be a true-false question or maybe a multiple-choice question about some of these phase changes, including melting and freezing. Melting and freezing, very similar to what I said about vaporization. You should be able to use the heat of fusion, as it's called here, to determine how much energy it takes to melt something or heat something up. By the way, that one question that everyone was having trouble with on the homework, where it was like, you go from -15 up to 220, how much energy does it take to get from here to there? There's not going to be anything like that on the exam. That was like a 20-minute long question, even for me. It was a long question to do. There's not going to be anything like that. The most I would do is give you one or maybe two of the sections from that question, because that question, I believe, had 5 different equations that you had to use to get the final answer. Well, really 2 equations, but then multiple uses of the same equation. There's not going to be anything like that. That's just too time consuming. I do expect you to understand why vaporization takes so much more energy than melting. So the main reason there being that when you're vaporizing something, you are completely moving it into the gas phase where the molecules are very far apart from each other, and so therefore have very, very little intermolecular forces. So in order to do that, you have to break all of those intermolecular forces, which is not something you have to do to melt something. Phase diagrams, essentially what I expect you to do is to be able to read one. So you should be able to read a phase diagram like any of these here. If I were to ask you what's the phase at 50 degrees C and 1 atmosphere of pressure, you should be able to say, okay, there's 50, there's 1, it's a gas. Something along those lines. Just be able to read and interpret a phase diagram. Okay, as far as critical or supercritical fluids, I just expect you to know that supercritical fluids have properties of both liquid and gas. I'm not going to get into any big details here or any, I'm not going to have you writing essays or anything like that. It's just a basic understanding of what a supercritical fluid is. And as far as the stuff about solids at the end of this chapter, the most that I would do would be to ask you to identify one of these 4 lattice structures. So we have simple cubic unit cells, body-centered cubic unit cells, face-centered cubic unit cells, and hexagonal closest packing unit cells. That would be the most that I would expect. There's other important information in here, like the little talk I gave about X-ray crystallography. It's a very, very useful tool, but it's a little bit beyond the scope of what I'd like to cover in this course and like to test you on in this course. So I'm not going to test you over that stuff, but I could just like cut and paste an image like this and ask, what is the name of this unit cell? And you would have to be able to tell, well, there's a body, an atom, in the center of this cell. So this is a body-centered cubic unit cell, and so on here. So, and then classifying the solids, don't worry about that. I'm not expecting you to be able to classify those, although you probably should be able to, but I'm not going to test you over that. So that was chapter 10. Chapter 11 is all about solutions. I do expect you to know the basic makeup of a solution. So a solution is made up of at least two things, solvent and solute. I'm not going to test you over all the different kinds of solutions that you can have. That was just kind of an introduction. I do expect you to understand the role that entropy plays in forming a solution. Again, we are assuming that entropy always favors the formation of a solution. Like I've said in the videos, that's not actually 100% true, but it's close enough to 100% true that we're just going to pretend like it is. Again, there are exceptions to almost everything in science. So we are going to just go ahead and ignore the exceptions here in this case. So understand that entropy wants things to mix together. And understand that enthalpy will sometimes want things to mix together and sometimes won't. So this is section here is talking about all the things that come into play in determining if enthalpy wants something to dissolve or not. So those would be the different intermolecular forces that exist between solvent and solute. So it's talking about here, talking about how things that have similar intermolecular forces will tend to dissolve in one another. So that could be a possible question where I give you two different molecules and say, is it likely that these two will dissolve? So this is just more talking about the solution process and the endothermic versus exothermic nature of those processes. If this was on a paper, if this was a paper exam, I might have you draw one of these figures out. I've done that in the past, but unfortunately this is not a paper exam, so I can't have you drawing stuff, which is kind of a bummer. I like a good drawing question. The supersaturated solution stuff, there's no need to worry about that. I'm not going to test you over supersaturated solutions. I do expect you to know the difference between non-electrolytes, weak electrolytes, and strong electrolytes. The main difference just being non-electrolytes don't break apart in solution at all. They stay as whole molecules. Strong electrolytes completely break apart. They completely dissociate in water. And then weak electrolytes are in the middle. Temperature effects. I do expect you to know that as you heat things up, solids tend to become more soluble in liquids. This does vary from one thing to the next, but in general, things do become more soluble, and that gases are the opposite. I expect you to know that gases become less soluble as you heat them up. And I also expect you to be able to use Henry's law. If you need to use Henry's law, I will give it to you on the little equation cheat sheet. But I expect you to be able to use this equation to solve for any of its parts. So I could give you the constant, and I could give you the pressure that the gas is under and have you tell me what the solubility is. Or maybe I could give you the pressure and the solubility, and you could work out what the constant is, one or the other. So that's just more of that. As far as different solution concentrations, I 100% guarantee you will have questions where you will have to convert either from one concentration unit to a different concentration unit, and or just from basic knowledge of the solution converting into a concentration unit. So I could have you converting from mass percentage into molarity, perhaps, or I could just have you calculate the molarity given information on the solution itself, not necessarily concentration data. I could just say you have this many grams of this stuff and this many grams of water. You know, what is the molarity, or what is the mass percentage or mole fraction? So there will be questions on the exam, at least 2 or 3. I can't actually remember how many I put on there, but there will be 2, maybe 3 questions, something like that, questions on the exam where you will have to work out the concentration of a solution in one of these units that we covered here. So either molarity, parts per million, parts per billion, mass percentage, mole fraction, or molality, any of those. So you do need to remember what each of those are, because those are not on the cheat sheet. It does not say on the cheat sheet molality is moles of solute divided by kilograms of solvent. You will need to remember that. Okay, as far as colligative properties, that was the vapor pressure lowering, the boiling point elevation, freezing point depression. If you need one of those equations to solve something, I will give you the equation. And I do expect you to be able to solve any of those 3. So if I give you a boiling point elevation question, maybe I tell you enough information about the solution that you can work out the molality, and I give you the constant, and you have to work out what the change in the boiling point is, or something along those lines. I do expect you to be able to work using those 3 equations, and I will give you those equations if you need them. For some reason it saved the markings from when I made those videos. Oh well. Osmosis, I'm not going to give you any questions over osmosis. It's a pretty cool phenomenon. Under certain situations, very useful, but I'm not going to test you over it. Same thing with colloids. If this was an on-paper exam, maybe I would give you a short answer question where you would describe what a colloid is, but I don't think that would work quite as well on a computer. Mainly just because on a piece of paper I can limit you. In my experience, if I don't tell you you only have this much space to write, students tend to write a whole paper for those types of questions. All right, last chapter here, kinetics. So here at the beginning we're just talking about kinetics in general, about how the rate can be measured by watching the change in the concentration as time goes by. I'm not going to have anything like this where I just give you a big table of data and you have to work out what the rate is. That does not mean that I won't give you a table of data in some question, just nothing like this, where you're going to need to work out the rates like that. Okay, let's see here. Oh, and I also will not give you anything where I give you a graph, and then I expect you to manipulate the graph in some way, or to read the graph in some way. I've had so many students over the years where I give you a graph, and I'll give you an equation. So I'll give you the equation for the graph. Let's pretend here that this is a straight line. So I give you a graph and it has a straight line on it, and I give you the equation for that line. And I've had so many students that just ignore the equation and try to draw lines on the table and try to work out the data like it's done here. Don't do that. I'm not going to have you do that. If I give you a graph, what you're going to do is just read the graph. You're not going to write on it. There's nothing that I expect you to pull from it other than the equation itself on the graph. So the main information that you're going to get from these is the equation, and then possibly you could use, like the axes. Like if you're not sure the equation or the data that you're looking at, you're not sure if you're looking at an integrated rate law or if you're looking at an Arrhenius equation. The axes might give you, or will give you, a clue as to that, but most of the time I just tell you. Most of the time I just say, here's some data for an Arrhenius equation. And so it's really just reading the equation that's on the graph. So don't try to extrapolate lines or anything like that, or to say, okay, well, if I have data point here, you know, that looks like it's about 56. Like, no, nothing like that. Nothing like that. Okay. I do expect you to be able to write out the rate like this. So be able to define the rate by the change in concentration for any reactant or any product. So if it's a reactance, you have negative at the beginning, -1 over the coefficient, times the change in concentration with time. And if it's a product, it's the same thing, just positive instead of negative. Okay. So now we're getting into the instantaneous rates here. Going back and forth, this is all just continuing to use this stuff here. Okay. As far as the continuous monitoring stuff, really all I expect you to know is that spectrophotometry is the most common thing that's used. I'm not going to, again, have you writing an essay about how a spectrophotometer works. Nothing like that. I do expect you to be able to read something like this. So I told you earlier there wouldn't be any big tables of data for you to determine the rates. I could give you a table of data like this. So I could give you a table of data where there's 4 or so different experiments, and you're given initial concentrations and the rates that are observed with those, and you have to work out, is it first, 0, or second order with respect to the different reactants. I do expect you to be able to do that. And it would be exactly like we did here, the exact same process. In the same way, I expect you to be able to use the rate law. So this is a mathematical equation here. I expect you to be able to solve for any part of that rate law. So if I give you enough information, you should be able to work out any one part of this. So if I give you the two reactant concentrations and also tell you the rate, you should be able to solve to find the rate constant, or, you know, flipping really any of those. As long as I give you enough information to find 3 of those 4 things, you should be able to solve for that 4th one. Okay, this is more the same stuff there. Integrated rate laws. I 100% guarantee you will have at least one question over the integrated rate laws. I think I put 2 in, but I'm not 100% sure on that. But there's 100% sure going to be at least one question over the integrated rate laws. And if I remember correctly, actually, I think I did one question where you just used the equation, and then I think I had another one where you interpret a graph, if I remember correctly. So again, I'm giving you tons of information here, because I want you to do well on these. I want you to study these, because these are perhaps the most important things in this chapter, are the integrated rate laws. They are the most commonly used, for sure. Maybe except for the Arrhenius equation. That maybe might be on par with the integrated rate laws. But like I said, if memory serves, I gave you at least one question where you have to use either the first order integrated rate law to, again, just use an equation like this and solve for one part of it. So I would give you enough information that you could plug in everything except for one, and you would have to do the algebra to solve for the last part, or do the same thing for the second, or the 0 order. Remembering again, that is not a negative sign, that's just a bullet point. So I would give you enough information that you could solve for one of those parts, And again, if memory serves correctly, I believe I also put in where you would have to do at least one question where you interpret a graph, like one of these, where I would give you a graph either of the first order data or second order data, and I would give you the equation on the screen, and maybe you have to work out what the rate constant is, or something like that. You have to work something out. I believe I give you one of each of those, I think. So don't hold me to that, but I know that 100% sure there is integrated rate law stuff on the exam. And I believe it is at least one using the equation and one using the chart, or using the graph, I should say. Okay. Half-lives, kind of similar to what we talked about before. Be able to use the equation for half-lives. And by the way, the integrated rate laws and the half-life equations and the Arrhenius equations, when you need them, I will give them to you. I don't expect you to have them memorized. I just expect you to be able to use them. So half-life is definitely something that could be on the exam, so be sure you know how to use the half-life for first order and half-life for second order, as well as zero order reactions. Alright, so now we're getting into the Arrhenius stuff here, and talking about the stuff that ends up being inside of the Arrhenius equation. I do expect you to know that orientation factor and activation energy are the two things that keep most reactions, most collisions from turning into reactions. So things have to be lined up just right, and they have to have the right amount of energy for reactions to take place. Which then again leads us right into, this is just more talk about the energy of activation. There it is, the Arrhenius equation. I guarantee you there is Arrhenius stuff on the exam. And I can't remember if I gave you both equation and graph questions or just one or the other, but there is 100% sure Arrhenius equation, at least one Arrhenius equation question on the exam. So know how to use this equation. The most common mistake students have with this is the algebra, dealing with this E, getting rid of that E. So make sure you are comfortable doing that, or be comfortable using this equation, either way, since they are the same equation, just different forms, as well as analyzing a graph. So I could give you something like this and have you analyze the graph to get some kind of data. Okay. So the last topic here, or the last main topic anyway, of this chapter is reaction mechanisms, and looking at either two-step mechanisms that have a slow first step or a slow second step. So that would be a fast initial step, and working out what the rate law would be from those mechanisms. You need to know how to do this. It will be on the exam. So I won't give you any more information than that, but I will just say that you do need to know how to look at a mechanism and work out what the rate law would be based on that mechanism. So it's exactly the same way we did here in the videos. So if you're like, oh man, I don't remember that at all, go back and rewatch the videos. The slow first steps, those are the easy ones, because you just take the reactants in that slow first step and plug them in, and that's all you need. And the fast first steps are a little bit more difficult, but they're not bad either. It just requires a little bit more algebra. Okay. And then the last thing here, just a little minor topic, is the catalysis. I do expect you to know that catalysts work by providing an alternate pathway by which reactions can occur. So they don't show up in the balanced chemical equation because they start off in the reaction and then they get spat back out. They don't actually get used up. And only things that are consumed or produced show up in the balanced chemical equation. So catalysts provide an alternate pathway with a lower energy of activation, and they're not consumed. That is the main thing that I'm looking for there, just a brief explanation. All right. So that is it for exam 1. This exam is going to be a little bit heavier on the kinetics than the other 2 chapters, but if memory serves, it's not so heavy that there's more of chapter 12 than there are the other 2 combined. It's not quite that bad, but it is a little bit heavier on the kinetics, but there's still plenty of the other stuff. Like I said before, I will give you any of the equations that you need, the kinetics equations, the freezing point, boiling point, elevation, and depression, Henry's law, all those I will give to you. I will also give you a periodic table with conversion factors for any questions where you might need those. That really only comes into play like on the solution concentration ones. Like some of those you need to convert between grams and moles, for example, so you need the periodic table for that. Let's see what else. So for the intermolecular forces ones, I will also give you electronegativity tables. You do not have to have those memorized. That will be included in the questions. I tried to put everything in as a PDF into the questions themselves. So you should theoretically be able to click on the link and it will pull the PDF up so you can see it. I don't think the testing centers will have issues with that. In my little message, because I have to send them something telling them how to access the exam, I told them that I was including those in the questions, so they shouldn't freak out when a new window pops up as you're going through the exam, as long as it is just those PDFs. If you try to access Google, well then yes, they will freak out and they will remove you from the exam. But as long as it's just those PDFs that are included, they shouldn't have an issue with that. I think most of the other information you can find on the exam page there. The main thing is just 90 minutes for the exam. You need to set an appointment beforehand before you can go in and take it, so don't just walk in and expect to be able to take it there. You do need to set an appointment. You'll still have to wear a mask and all that good stuff, so you can't you just need to act like you're going into class, essentially. Bring everything that you would need for class, including writing utensil and calculator, but do not bring your own notes. Those are not allowed. All right, I think that is it. I will be on the Collaborate classroom tomorrow. I kind of doubt very many of you will be able to watch this before then, but for those of you that do have time to watch it before the Collaborate session tomorrow, feel free to come with your questions. And for even those of you that are watching this afterwards, hopefully you still came with questions to the Collaborate session. Good luck, and I will see you all later.